O plus the probability of getting a type A, because they have nothing in common. They do not overlap. So the probability of getting a type O is what? Good. Here's my type O. I don't care if they're positive or negative. 184 out of 409. Good. What's the probability of getting a type A? 164 out of 409. And this is another reason why we keep our denominators the same. We don't reduce yet. Then when you add these guys up, you get a lot more. People either are going to be A or O, have a very strong probability of this happening. If you want to leave it in a reduced fraction, you want to leave it as a decimal. I like the decimals. I tend to reduce everything to decimals. Right? That's a pretty strong probability that this person that I select is going to have a type O or a type A. O, I think, is the most common one. It is the highest one. A must be another pretty common one. Okay. Now, find the probability that the donor has a type B or is an Rh negative. Now you ask yourself this, can a person have a type B and be Rh negative? Yes. So are these mutually exclusive? No. So there's an overlap here. So I'm going to take the probability of getting a B plus the probability of getting an Rh negative, and I'm going to subtract the B and Rh negative, because I'm going to count it twice. You're going to see it in the chart. Here's my B. Here's my B's. Here's my Rh negatives. Can you see where they overlap? We have an overlap here, right here. This is where they overlap. So therefore, what is the probability of getting a, which one are we doing? What is the probability of getting a type B? I'm going to have to bring it up here. What's the probability of getting a B? 45 out of 409. What is the probability of getting a Rh negative? Now here's the tricky part. Where do they overlap? 8 over 4. I've got to use this. I can't use 45 because it's in this one and it's in this one. I got to use 409. It kind of stands to reason because your denominators all should be the same. So watch what happens. This is why we do this. In this category of B, I counted these positives, I counted these negatives. I got 45. In this category of negatives, I counted this one again, this one, and I got a 65. I technically counted this guy twice. In this row, in this column, and in this row. So therefore, I have to remove it. I counted it twice. It's the same person. So this is where they overlap. If you picture a Venn diagram, here's your B's, here's your Rh negatives. These are the guys that are B and Rh negative. That's my Venn diagram says. They overlap there. Okay? You feel that? That's the tricky part. So I want you guys to try it for us right underneath it. Let me see if I move this down, I won't have the chart, but you have the chart. So you're going to try it 4. Try it 4 says, I need the chart. I'm going to put it right here. These are the ones you're trying. These are the ones you're trying, the ones underneath this. I just moved it so we can see the table. So take a moment and try both of those. Okay, so for the first one, Devin, give me your equation for this, your formula for this. 45 over 409, so he's doing the probability of B plus the probability of AB. Do they overlap at all? No. You have B, you can't have AB. So B has a total of 45 over 409, and AB has what? AB has 16 over 409. So what do you get? Did you get a decimal? 149. Thank you. Okay? That one, mutually exclusive. They cannot happen at the same time. If you have type O, you can't be any other type. Type B can't be any other type. Okay, the probability that you're type O plus the probability that you're RH positive minus what? O and RH positive. Good. So let's take a look at this. Here's my O's. Evangelise, what did you get for O's? 184 over 409. What did you get for RH positive? Good. 344 over 409. Now, where's your overlap? Type O, the person that is this, I counted them here, and I counted them there. So, minus 156 over 409. Good. What'd you get? 372 over 409. And what'd you get for a decimal? That's fine. That's pretty high. Type O type O positive is probably your best, like your biggest one, your biggest seller here. Okay, does everybody get this part when they're mutually exclusive? I love the charts because I think they're so much more easier to see. Otherwise, probability is very abstract, and if you're not like visualizing these things, you're trying to make like a little scenario in your head, it's hard to figure it out. So when they do a chart like this, it's nice. All right, there's one more I want to do because this has a good case with the only I don't have the chart here, so we're gonna have to use your book for this. And I should put this in my notes. On page 161, there's a little graph of a football field. Monday will help us through this one. Okay. We're going to use this figure at the right to find the probability that a randomly selected pick is not a running back or a wide receiver. I don't want him to be a running back or a wide receiver. He can be anything else. So should I add up all the other things? So if they told us this is a breakdown by positions of 253 players. I want the probability that he is not a running back or a wide receiver. Can a person be a running back and a wide receiver at the same time? No. So these are mutually exclusive. But I don't want these guys. I want everybody else but these guys. So what should I do? Subtract from what? From the total. Why not? Why not use my complement case? Good job. Dave. Wonderful. So now, I'm going to find the probability that this guy is in fact a running back. How many running backs are there, according to this chart? 21. And how many wide receivers are there? 33. So if I do this, don't I get everybody who is not a running back or a wide receiver? I get everybody else. This is like my complement case. Now you have two ways to do this. You can do it with the numbers, or you can set it up 1 minus the probability. So sometimes when they give you the numbers, maybe that makes a little bit more sense than finding the probabilities first. I think they find the probabilities and then they subtract them. But we're going to do it a little differently. They do it the 1 minus that. So we're going to just do this a little bit differently. So the fact that we do this and we add these together gives us 253 minus 54, and then we can put this over 253. Okay, so it's kind of helpful to take those out of the mix and then figure it out. Okay, find the probability that it is not a linebacker or a quarterback. We would do the same thing. We would pick up, can a person be a linebacker and a quarterback at the same time? Heck no, right? Offense and defense, and that could be either offense or defense, right? So it can't be a quarterback and a linebacker. So these, again, are mutually exclusive. You add those together, subtract them from 253, and then build your probability. It's easier than adding everybody else on that chart. Plus, when you go through a chart like this, they kind of spread them all over, you're more apt to miss it. And the chart itself told us the total right at the top, so we didn't have to bother adding them all up to get your total. Do you have any questions on this at all? No? Okay, so I'm going to give you some to do, and we're going to do them today and a little bit tomorrow. And I want to wrap this up by tomorrow so Wednesday we can have a little fun. Let's see what I want to give you here. So, okay. I think this is it. 7, 11, 14, 15, 18. Okay, so you have probably a good 20 minutes, 25 minutes today, and we'll take at least half of tomorrow's class, if you're working. So you need to be working on this. If you want to work with a partner on this, that's fine, but I need to see work being done. If for some reason you don't think you'll finish it between now and tomorrow, that gives you like probably 40 minutes to do this little section. If you don't think you'll be done, then do some at home. But I think you should be able to get this all done in this little time. The first like 4 or 5 are just asking you if they're mutually exclusive or not.